Hi again. Let's continue our discussion on insurance or insurance benefit. So if you recall, we did the pure endowment, we did whole life insurance, we did term insurance, we did endowment insurance. So now what we need to look at another term called deferred insurance. So deferred insurance, the basic idea here, you have a life age X and you want the insurance to start at X plus M. So you don't want it to kickstart now. You want it to start at X plus M. Why? It's simply maybe, for instance, somebody is considering employment in high-risk country that he will accept or she will accept the job. He accepted or she accepted the job offer, but it will start in a year from now or 2 years from now. So I have insurance that starts in 2 years from now, or maybe I wanted the life insurance once I have children. So like it's basically I don't want it to start now. I want it to defer it to start at later stage. So it's the same logic. At this point here, this is AX plus M, right? This is life insurance at this point here, right? But we want to evaluate it here. In actuarial mathematics, to bring anything back to here, we need to multiply it by the actuarial discounting factor. And remember the actuarial discounting factor, here we have M, so it should be multiplied by MEX. M or N, but for us we used M here. So, but we have a specific notation for deferred insurance, similar to deferred mortality. It's the same logic. So those notations, they make sense if you just follow the logic. So we're looking at insurance and payable at time of death. So if death occurs anytime here, then $1 will be paid here, paid at time of death. And this insurance is X, but instead of writing X plus M, we will have similar to the deferred mortality, but now this deferred insurance and deferred for years M. So just to make sure we understand what we mean here, this is the deferred period. This age, again the same thing, this one continuous or payable at time of death. And this little bar here, it says like deferred. It tells us it's deferred, right? It should be subscript, everything here, right? It's tells us it's deferred, right? So this is deferred insurance. So now let's relate this one with this one. So M, the deferred for M period of AX, insurance paid, the unit of insurance paid at paid at time of death, but deferred for M period. How we can relate it with this AX plus M, because it's here. Simply in actuarial mathematics, always remember that when you discount back by MEX. So you need to multiply by MEX. If you want, you can write it also just what is MEX is, like here AX plus M. What's MEX is not only it's not only the present value of VM, it's actually you add probability to survive, because actuarial present value, you need to have probability for somebody life X to survive to age M, right? Can be also written MPX instead of V. You can write it C lambda M, a delta M, AX plus M, right? This is the deferred insurance. But let's take one example. Let's take example here. Same example. Let's take the same, or let's take uniform. So imagine that you have uniform distribution. X is uniform over 0 to 100, right? And we wanted to evaluate 10 A30 continuous, right? And simply we know what is this. It's we can write 10 because it's deferred 30, and now the individual we shift it to 40, right? Because I mean, you can think about it this way: 30, 40. So we have A40, we need to bring it back to 830. So how we bring it back? We use the discounting factor, right? So because this is uniform distribution, 10 E30, it's let's say lambda, the same lambda we use is 0.5%, but the same one we use. So now E lambda, which is 0.5 discounting factor, multiplied by 10, right? Then we need, this is uniform distribution, so somebody like the up to 100, because uniform omega is 100. So somebody to survive 40, if you remember TPX, what it is. So it will be TPX surviving to 40. It will be like if you would write it here, TP30, it will be 100 minus 30, which is 70, minus T divided by 70 for uniform. So this one, if you take 10, it will be 6 over 7. So this is now the discounting factor, actuarial discounting factor. Now we need to multiply this one by A40 again, which E minus 0.5 multiplied by 6 over 7. And the A40 for uniform distribution, if you remember what it is, A40 for uniform distribution, and this you should know the formula now, 1 over omega minus x, which is 1 over 60, multiplied by an unity certain for 60, right? So let me use a calculator right away to compute this one. And let me write it also here. So 1 over 60 multiplied by A60. This one is 1 minus E minus lambda multiplied by 60 years. Sorry, delta divided by delta. I keep saying lambda. Anyway, so let's calculate this one. If you have your calculator, if you want more time, you can compute it yourself. So I use this calculator, so I calculate everything at one step. 1 minus E minus our delta is 0.5105 multiplied by 60. Oh, what did I do? Divided by 0.5 divided by 60 and multiply by 6 divided by 7. Now multiply by E minus 0.5, because 0.5 it comes from 0.5 comes from 10 multiplies by 0 by the lambda. So I got, so my calculation is 164,667. So the deferred annuity, this one is, we are like this deferred annuity is 10 deferred for 10 years will be this value. Exponential is easy. Let's take another exponential, example 2. Now if life x is now exponential distributed, so x is is exponentially distributed. We need mu, and let's take mu is 0.5%, and what is mu? Mortality rate, and delta is 0. So let's compute the same one. 10 Same logic is 10p30 multiplied by E minus delta for 10 years multiplied by now A40. And this is easy because this is uniform distribution. So 10p3, it's like you would have, if you compute for 10 years, so minus and this 10 years, so it will be 15 yeah, multiply by 10. So you have, well, let's do it again, multiply by 10, and now you have E minus 10, sorry, 0.1 multiply by 10, and A40, this is life insurance for 40, this is mu over, which is 0.5 divided by 0.5 plus 0.10. It's easy. So everything here we can think of it as 1/3, and this is 10, 1, and this is 5, so 1.5. So E minus 1.5 multiplied by 1/3. E minus 1.5 divided by 3. I got to be the answer, I got 0.0743. So it's easy. 437, yeah, which is 4. Right, so very easy. So there is nothing complicated here. Now let's move a little bit into something, how we relate things together. So now let's look at this now. Let's look at some relations. So this is your x, and you have x plus m here, right? You can compute here, right? This is easy to compute. You can compute here ax, right? And imagine now if you compute for this period, you compute ax n. Want you to remember this one. Sorry, for term m. This is for m years. For term m, if the life dies within this m years, will receive $1, and this bar tells us at moment of death. How we can relate these three together? Again, it's similar to interest theory, but we need to have the actuarial discounting factor. So remember, this one is evaluated here already, but this one is at different time. This x, it tells us that the evaluation point is at time x. So we know that these are at the same time horizon. So we have ax bar is equal to ax. There is no need to discount, because this one is already discounted, right? It's already at age x. But this one here, it's at age x plus m, right? So this one at age x plus m, we need to bring it back. How we can bring it back? We need to remember that now this one, to bring it back, we need to have the actuarial discounting factor. The actuarial discounting factor MEX, right, multiplied by AX plus M. There is logic here. If you get it, it's very easy. Similar to interest theory, if you are good at interest theory, it's the same logic. The only difference here, MEX, it includes also probability, right? So let's take one example here. I don't want to calculate everything because we already calculated them before. Given, so you are given some information here. So we already calculated this one for uniform distribution at 10 and give you one value here. We calculated it to be 1124. We calculated also this one, TP30 V10. This one we wrote it. It can be also written AX no bar here, right? The same. This one we computed it. If you go back, it's 0.5199, and we computed also A40 to be 0.31. I'm looking at my notes because we already computed this before, right? So now the question is find the insurance value for a life at age 30, and you given this information. So simple, right? Because now this one at the same year like this one, so A30 110. Now we have A40, but this one we need to discount it back. This one is 40, it's not the same year. So in interest year, in actuarial math, you need to have the same year. So this one you can do it in 10E30. So you bring it back. And once you do that, then it's straightforward. So it's 01124 plus 5199, right? And then this one is multiplied by A40, which is 3167. And now let's do the calculation. 4 plus 0.5199 multiplied by 0.3167. We got 0.27705. It's simple. So this relationship, we need to remember it. It's very important, right? Or the more general form is this one, because it's very useful. Let's take a more challenging question, little bit harder, but it's easy if you know this relationship. It's again actuarial mathematics, really nothing very complicated. It's not really hard mathematics, but it's because you have lots of notations, so that to keep a track of them sometimes a little bit confusing, especially at the beginning, but as you practice more, you will become better at it. Let's take one example. Now let's be given, and this is quite interesting one. So we have the delta t. Delta is not a fixed value here. It's actually, it has two values, 0.4 and 0.5. And 0.4 if death occurs between 0 and 10. But if death is greater than 10, or t is greater than 10, then we use 0.5, right? So it's like kind of a step shifting in this one. Same logic for this question. We have mortality also, it has a shifted mortality. So mortality here is 0.06, sorry, and 0.07 for the same period. For t is t is greater than 10. It's very simple. I mean, it looks difficult, but it's very simple to handle them if you know the relationship I gave you the last one. And the question is find this one. And very important to know that we need to split it here, because we have two, you have a period at time 10, it changes. So it's easy if you recognize that this relationship, you can write it this way. Can write AX plus because this is here x plus 10. Why we need to do this? Because again, there is a split here. There is a shift in mortality, a shift in force of interest at time 10. So it's better to deal with them separately, because this is unique area here. because here you have mu, you have delta is 0, 4, and mu you have it here is 0, 6, but here delta is 0, 5, mu is 0, 7. That's why we split it, because we need to deal with them separately. Once you know this, it becomes easy. This one, and well, what form of this relationship here? It's clearly it's the exponential distribution, because we have mu. So in exponential distribution, if you recall, this is something that you can remember quickly, mu plus delta, but because it's term and the 1 over the x, then you have 1 minus e, my 1 now mu plus delta for 10 years. You don't need to integrate anything because you should memorize it by now. Now plus, now 10ex, and this is exponential distribution. Remember the 10ex, we're still here, we're operating here, we're not here, we're still in the 10ex. Survive this period. Well, I mean this exponential distribution, so it's e minus, we add them up, 0, 4 plus 0, 6, because you need to survive both. You need to survive and you need to discount, so it's both multiply by 10. Now let's look at this one here, this uniform distribution. Uniform distribution, it's mu at mu plus delta, but this mu is, we need to take now from this side, and this mu you need to take from this side, right? So we need to be careful about this one, not to confuse them. Let's write what we wanted here. So here is, we take mu, it's 0.06 divided by 0, 1 multiplied by 1 minus e minus 1 plus e minus 1 multiplied by, look at now the mu is different, multiplied by mu, which is here is 0, 7 divided by 5 plus 7 is 12, 0, 1, 2. Now simple, if you do the calculation quickly, I'll do it quickly. So you have 1 minus 0.6. So this term, I usually keep it in the calculator, but just for you. And it's very important to keep in the calculator because you don't lose any decimal. It's important to keep all decimals in actuarial mathematics. Now the second term is second term is 0.21459 plus, now we add them up, you would get 0.59386. Okay, now I will we finish this. Now we have I already placed a long assignment, so some questions, so it's good to practice. Some of them I solved them because they are a new concept, so it's part of the learning. Others I just put the answer, so it should be easy for you to verify the answers. The ones that require more work, I already solved them for you, and then in the office hours, if you would like to go over those questions, they're important. So now, like as you see that I explain the concepts and some examples to make us understand the concept, but the more challenging questions are I post them as problem set, and it's very important to do them because more or less the exam should resemble the questions you see. All right, we'll see you again.